Hi, so here we are. Hopefully you tried these problems and you are going to check either my key or if you want to check the video because they were hard for you, here we go. So I did a little something different. Sometimes they don't tell you about probability when you're doing problems, but they tell you about the odds. Okay, and the odds mean that for every 3 wins, there's 1 losses. There's one loss. So that means that the probability that the varsity wins, Okay, so let's do the probability of varsity winning. So the probability that varsity wins a game, 3 chances to 1, meaning out of 4 chances, there's a 3/4 chance that varsity wins a game. Okay, now let's see what the problem says. They're going to play a 5-game series. So you're like, oh, we're doing something again and again and again. And the chances that varsity wins is always the same. So you're like, oh, it's binomial theorem. Okay, so what do we want to have happen? We want varsity to win 4 games. So that's 3/4 for them to win a 1 game. We want that to happen 4 times. But they're playing a 5-game series, which means they have to lose once. And if the chances of them winning is 3/4, then the chances of them losing is 1/4. Okay, now we need our counter. Because remember, this describes one branch. Like if you're doing win, 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 and then lose, and you're down here. But these 4 wins and 1 loss could have happened elsewhere in the tree. So we need our counter. Okay, so let's see. We've got 1, 2, 3, 4, 5 things happening. So out of those 5 things, we have to choose the winners, and we only want 4 of them to be winners. So here is that probability. Now I want you guys to be better at calculating things too. So let's just kind of think. You could type that in your calculator, but let's write it in a different form just so that we can keep on working on our number sense. Okay, so 5 choose 4 is how many ways you can grab out 4 things from 5, which is the same as leaving 1 thing behind. So that has to be 5. And then if we sort of thought about those fractions, I would have 3 to the 4th, and I would have 4 5 times. And you guys type in your calculator, but I get that that's about 40%. All right. Okay, now let's look at the next one. Okay, there are 5 red. So 5 red, 10 blue. We're going to grab out 3 marbles. So that, even though they didn't say it, if you're going to grab it out, that means we didn't throw them back. This means this is without replacement. Okay, so we're grabbing marbles out. We're picking a subset. So you're like, oh, can't use binomial theorem. So let's see if we use combinations. So if we're going to, we want 2 to be blue. So if we're going to arrange the marbles on our floor, and I hope we're back in North 317 before the end of the year so we can share that space again. How would we do it? We would put the 5 reds in one pile. We would put the 10 blues in another pile. And a winning is we are going to grab out 3, and we want 2 of them to be blue. So we're going to go over to the blue pile. And out of those 10 marbles, we're going to choose out 2 to be blue. But since we wanted 3, we're going to have to go to the other pile, which has 5 in it, and choose out 1. And that's going to give me my 3 marbles that I want with the right color. And we're going to divide by counting the same sort of way. So how else could we grab 3 marbles? We could just go to all the marbles in a big messy pile and choose out 3 of them. And that I typed in my calculator. And I got 49.4%. Okay. Okay, let's do one more. Okay, so this is one of the ideas we started with. How do you know if events are independent or dependent? You have to compare conditional probabilities. Okay, let's say that this is A, and this is B. And since we're doing 2 dice, sometimes that's just easier just to sort of make the table. 2 fair dice, there's 6 sides, so you draw and I'll draw. So what I have now is a picture of the 36 equally likely things that can happen. And now I can just use counting to help me see. Okay, so let's see. So let's do a little color annotation. And let's say that we want a sum to be of at least 7. I'm just going to put a little star. So I think on this diagonal, the sums are 7s. That's the most likely sum if you play any dice game. And so everything on this side is more than 7. Remember that at least means 7 or more. And you guys count on your paper or on my screen, but I think I got 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so the probability of getting at least 7 is 21 out of my 36. I think I could divide by 3, so that's 7 12ths. Now, the hard part with conditional probability is you have to compare it to dependence. You want to compare the same event, probability I got 7, knowing that I have a pair. So this time I know I have a pair. So everything in this table didn't work, just the pairs. Okay, so let's see what the pairs are like. Let's change the color and let's do pairs with circles. Okay, so the pairs, we've done this before, the pairs are on the diagonal. Okay, so for this probability, I know that I couldn't pick from all of the boxes, all 36, that I know I had to be in one of those 6 boxes on the diagonal. And out of those 6 boxes, only 3 of them do I have a sum that's 7 or bigger. So this probability is 1/2. Okay, so what are we going to say? We're going to say that 7 12ths is not the same as 1/2. Therefore, the events are dependent. Now, you could use a different base event. So let's kind of, if you wanted to think about it a different way, let's see if we got a little bit of a lag. Hang on. Let's see if we can think about it a different way. Okay, so let's say the probability we get a pair, well, that's 6 out of 36, which is 1/6, versus the probability we got a pair, knowing that we got 7 or more. Okay, so this time I know that I got 7 or more. It's easier for me to do the denominator first. The 7 or more were the 21. And then we know we have a pair. Oh, sorry, we know we have a 7 or more. There's only 3 of them. This is 1/7. And again, these two aren't equal. So we say the events are dependent. So it doesn't matter which one you use as your base. You get the same answer either way. That's my dog Tinker.